All right, g'day guys. We'll get started today. Chapter 9, as you can see, is entitled Integrals over General Regions. I mean, of course, we're talking about double integrals here. So this is just continuing on the discussion that we started this week from the previous two lectures. I'll just remind you, we started off with defining the double integral, and we considered the problem of finding the volume below a surface of a very special form, that is z equals some function of x and y, and above some region in the xy plane. We started off really simple, where the region in the xy plane was a rectangle. Okay, last lecture, we then saw that given the definition of the double integral, it's great news. We don't have to evaluate limits every time to determine what the value of the double integral is. Instead, we've got this really useful result known as Fubini's theorem, which allows us to transform the double integral into an iterated integral, which is relatively easy to solve. Okay, it's just a matter of evaluating one integral after the other, working from the inside out. Okay, but all the discussion up till now has only been where the region of integration is a rectangle. And so in today's lecture, I want to introduce to you how we can generalize this to more general regions in the xy plane. And what we're really going to focus on is not looking at the completely general case, although we will be able to deal with such a case where the region is bounded by finitely many smooth curves. So we're not considering particularly complicated regions in that sense. But instead what we're going to look at are the building blocks of how we can generalize to any type of region bounded by finitely many smooth curves in the xy plane. All right, and it turns out there are two types of these fundamental building blocks called, conveniently, I guess, type 1 and type 2. So that's what we'll see today. Look, just to start with, on page 60, we have a formal way of connecting these double integrals over more general regions in the xy plane to the rectangles, that is, to the situation that we've seen up till now. All right, so all this discussion here is just really the formal connection with that which was introduced in Lecture 7. So I'll just say the formal connection with Lecture 7. Okay, so I'll just go over this quickly. So if we've got some general region D, now really I am here just saying by general region, I still mean a region that's bounded by finitely many smooth curves. Okay, so it's general up to that comment, up to that qualification. So to define or to find the double integral over some general region, call it D. I usually use D for domain, by the way. So general region D instead of just a rectangle. What we do is consider a rectangle which encloses that region. And if we're interested in defining or finding the double integral of this function little f over that region D, then what we can do is define a new function, capital F, that's just related to the function we're actually interested in this way. So it's a very simple identification here. So we just define the output of this new function, capital F, to take on the same values as the function little f if the input values lie in that domain, so lie in that region in the xy plane, or 0 otherwise. Okay, and if you think about defining the double integral, the way we've defined the double integral in terms of Riemann sums, then these two double integrals must clearly match up. Okay, so if I always have to watch when I use the word clearly. All right, so let's just have a look at a diagram. that will hopefully make that clear. So we've got some region, call this the region D in the xy plane, and we want to know how to evaluate the double integral of some function little f over this region D. Then what we can do is define a rectangle, and the edges of this rectangle, they don't particularly have to just touch the edges of D. It's just the way I've drawn it. So this rectangle here, this is the region that I've called R in this double integral on the right-hand side. So that's the domain, or rather the region in the xy plane over which this right-hand integral is taken. Okay, and so all points inside the rectangle R and inside D, then the value of the function capital F just matches up with little f. But everything in these parts that lie inside the rectangle but are not inside D, this function capital F takes on the value 0. So you can see imagine what that function looks like as a surface. Imagine what the graph of that function looks like. Imagine the z-axis coming out of the screen here, and we've got some surface defining or representing the graph of this function little f. Okay, then that surface could be something non-trivial directly above the region D, but the surface is just 0, so z equals 0. In other words, it's just the xy plane itself over these shaded regions that I've got in the corner. Okay, it turns out such a function is still integrable, and it turns out the Riemann sums, or the limits rather, of the double Riemann sum still exists. Okay, so we can still talk about the double integral on the right-hand side. Okay, so that's just a formal connection with what we've seen so far. All right, it's just one way to think of it in terms of Riemann sums. But actually what I really want to talk about today, and this is what I'll spend most of the time talking about, is the variant of Fubini's theorem when dealing with a more general region in the xy plane. Okay, so the strategy here is to consider the building blocks, right? Only the building blocks. We can deal with much more general regions after this, and I'll show you an example of one. So we'll start by considering two types of regions. The first we call type 1, right? Not particularly exciting, but nevertheless, just to distinguish between the two regions. All right, so here's how we define a type 1 region. So a plane region D is of type 1 if it lies between the graph of two continuous functions of x, as in this diagram we've got here. So this curve at the top would have equation y equals g2 of x, and the curve at the bottom, y equals g1 of x. Okay, and the region is also then placed between two vertical lines representing the lines x equals some constant a and x equals b. All right, so now remember the interpretation of Fubini's theorem in terms of volume below the surface. Remember what we were considering last time we were considering first estimating the volume below that surface using slabs. Okay, so that's exactly what we're going to do here, right? Consider the volume below some surface. So say we've got some function little f of x and y, and we've got the surface with the z-axis coming out of the screen. So z equals f of x, y is some surface sitting out here. Okay, and so first to estimate the in such a case, for such a region, right, that lies between these two continuous functions of x only, what we can do is divide the x-axis up into subintervals, right? Zoom in on one subinterval and choose a representative point. I'll just call it x star. Choose a representative point in each subinterval, okay, and then approximate the volume below the surface and above this small rectangle of width delta x, so that's a rectangle in the xy plane. And then what we're going to do is evaluate the function little f of x and y at this representative point x star. So it's actually going to just be a function of y, right, as we move in the vertical direction, as we move in the y direction. Okay, so in that case, that'll define a curve that lies on our surface. All right, and then we take that curve to define the top of our slab. So look, at this point, over this rectangle that I've drawn here, and I do apologise, but I mean, I should probably try and prepare these three-dimensional pictures a little bit more, but in advance. But essentially, what we're going to be doing is taking slabs, so it might look something like this. All right, I'll just shade in the side of the slab, representing the cross-sectional area of that slab. So it's, I understand it's a bit of a perspective issue here, but what I really want to do is pick up that slab and place it onto that rectangle I've drawn over the region, inside the region D, I should say. Okay, so one thing, so the bottom of this rectangle is actually given by the value for y, which is just g1 evaluated at x star, right? And the top of this rectangle is just going to be the value of that function at x star. So g1 of x star is at this point, g2 of x star at that point. And so what we can do then is work out the volume of that slab. Remember, it's just going to be the width of the slab, which is delta x, multiplied by the cross-sectional area. Okay, so what's the cross-sectional area? Well, we went over this in the last lecture, in Tuesday's lecture, but now for this particular case, the cross-sectional area, so it's just going to be a definite integral now of a function of a single variable, right, where we take that function little f of x and y and evaluate it at this point x star, but we're letting y roam over all values between g1 of x star and g2 of x star. Okay, so all we're really doing here is just calculating the area below a curve, right? And between the, well, in this case, the xy plane, but it's a line in the xy plane parallel to the y-axis. Okay, so it's pretty much the same problem as just area under a curve is a definite integral of a function of a single variable. And so in this case, now we're integrating with respect to y between this value, g1 of x star, and the upper bound will be g2 of x star. All right, so that's going to give us the cross-sectional area just for that one slab that I place over this rectangle. But now you see what's going to happen, right? As we move along that interval to the neighbouring sub-interval along the x-axis, the height, what can I call it? The length of that rectangle is going to change depending on what these two bounding functions are doing. So, for example, if we're over here now and we make an approximation to the volume under that surface using slabs, you can see the base of that slab will be a different rectangle. Okay, so the volume of that slab is going to change in this direction as well now, not just at the top, depending on what the surface is doing. All right, so you can see it's a little bit more complicated than just considering the volume above a rectangle. But nevertheless, we can still do this. And the result is summarized here, which is the same, using the same argument that we used to arrive at the result of Fubini's theorem. Okay, namely that we end up integrating, so you can see this expression is still what we call an iterated integral, but now you can see the bounds of the inner integral, which is an integral with respect to y, the bounds are functions of x now. Okay, and that comes from the fact up here that the cross-sectional area of each slab And remember, ultimately, we take the limit as the thickness of those slabs go to 0, so we take more and more slabs and get a better and better approximation until the thickness goes to 0, or equivalently until the number of slabs go to infinity within this, this finite region. Okay, so that's just the cross-sectional area, that inner integral, and then we're just integrating over all of those terms. In other words, we're just summing up over all slabs under the surface. And in the limit as the thickness of those slabs go to 0, it's Fubini's theorem at work here. We get the double integral is just equal to this iterated integral. Okay, but now the inner integral is a function of x only. Okay, so I've got a couple of examples, just 2 examples of diagrams which can be represented as what we call type 1 regions. Okay, so just remember that the type 1 regions are those which lie between 2 constant values of x and 2 continuous functions of x. All right, as I've got up in this diagram. So between 2 constant values of x and these 2 curves, which are the graphs of functions of x. Okay, now I'm particularly fond of using this notation, as you may have gathered, which, as you can see, is a description of the region, but also it allows me to read off the bounds of the iterated integrals. So you can see the bound. And, well, actually, the way I think about this, I would read this expression as saying D is just the set of all points x and y, well, with coordinates x and y, such that the x-coordinate lies between these 2 values a and b, right? So just specifying that bit of information is just saying that the region lies somewhere along this infinite strip, right, between x equals a and x equals b. And then we provide the additional information and say, given a value of x between a and b, then y will lie between whatever those values are given by the functions g1 and g2. Okay, so that's the way to think about that expression for this case. Now, just to show you an example, just staying with the discussion on slabs. So this example isn't in the workbook, but look, I'll post this when I scan it in. I'll have to put this on the other screen. So we're considering the volume above this region in the xy plane between x equals 0, y equals x squared, and y equals 1, and below the surface z equals 4 minus x squared minus y squared. So here I've just got a diagram. It's a 3-dimensional diagram that I've produced using MATLAB, but I've just started by looking at what the region is in the xy plane. Do I have a pointer somewhere? Is that a pointer? I have no idea what this is. Anyway, this will do for the moment. I'll have to be very careful. It looks like it's got some electronics in there. Anyway, you can see there's this region. So this part here is, I haven't labelled the diagram, but that's the curve y equals x squared. Here's the line y equals 1. And we've also got x equals 0, which is the y-axis. Okay, so there's the region just in there. That's the region we're interested in the xy plane. Okay, so we're interested in finding the volume above that region in the xy plane and below the surface, z equals 4 minus x squared minus y squared. So all I've done here is just add part of that, or the part of that surface in that sits directly above that region in the xy plane. Okay, now regarding the approximation using slabs, all I've done here is just work out an approximation. I mean, not even using numbers. This is just a visualization. What I really want you to focus on when watching this is look at how the base of these slabs, so here's one slab, so just using 4 slabs as an approximation, so 1, 2, 3, 4, you can see how the length or the depth, I don't know, what can I call that dimension? So I mean the length of that side here, you can see how that's changing as we move along the different intervals in the x direction. Okay, the different subintervals. So anyway, there's just using 4 slabs what the approximation would look like if we use 8 slabs. So we're getting thinner and thinner slabs here. So each case in our approximation, so now with 16, each case to work out the volume of the slab, it's just going to be the width of the slab multiplied by the cross-sectional area. And so now we're just using more and more slabs in the approximation. Okay, and finally, I think this is, there are 32 here, 32 slabs. So quite thin in the context of this diagram. More and more slabs, and we get a better and better approximation. But you can see what's happening. You can see how the base length of the rectangle of those, the base of those slabs, the dimensions are changing as we move along in the x direction. All right, so that's all I just wanted to show you about that example. Now I'll just carefully place this back where I got it from. All right, and so that's just how we approximate using slabs. I hope showing you that visualization, I hope I can I get the message across. I'm not actually going to calculate that example. All I wanted to do is just show you what the slabs look like. But over the page now, there is an example just to indicate how these calculations progress. So in this case, we're just being asked to find this double integral, or to evaluate this double integral, where the region of integration, D, which is the region in the xy plane, lies between the parabola y equals x squared and the line y equals x plus 2. And actually here I've drawn I haven't drawn it, I've used MATLAB to produce a 3-dimensional diagram of the solid that's under consideration here. All right, just interpreting this in terms of volume below a surface. All right, so this is one thing that you should be starting to get the idea now. With a double integral, there are 2 important bits of information. Right? There's what is the function that we're integrating, and what is the region of integration. Right? So there are 2 things that are important in evaluating a double integral. In this case, the problem is just stated as evaluate this double integral. So we already know what the function is we're integrating. It's not stated as a problem of find the volume of this solid blah, blah, blah. Okay, so we already know what the function is that we're integrating. However, we need to work out an expression for this region so that we can apply Fubini's theorem. Right? And generally, this is always the hardest thing we have to do in these calculations. So look, for that purpose, to work out what the region looks like, we just draw a rough diagram, or we can draw a rough diagram. Whereas in the question, we're given that the region of integration, so that's the region in the xy plane, lies between the parabola y equals x squared. So here's y equals x squared, and the line y equals x plus 2. So that'll look something like this. So there's the line y equals x plus 2. Okay, and so the region we're interested in is in here. So now what I want to do is first identify it as a type 1 region, right, what we've defined before, namely saying that the region sits between two constant values of x. So I can actually see that the leftmost point of this region corresponds to whatever that value of x is, and the rightmost region corresponds to this value of x. Okay, so I can actually start by saying this is a type 1 region because I can see it sits between x equals one constant over on the left and x equals another constant on the right, and sits between these 2 continuous functions, or the graphs of these 2 continuous functions of x, namely x plus 2 and x squared. Okay, so I guess the first thing we need to do then to identify the x coordinates of these points is work out the points of intersection of those 2 curves. All right, and to do that we can just match up the y values and set x squared equal to x plus 2, right? It's just a quadratic equation in this case, and we end up with the two values being 2 and negative 1. Right, so here's x equals negative 1, and here's x equals 2. All right, so now what I want to do is work out, so I've got the bounds for x. So in fact, this is what I'll do for the region D. I'll represent it as the set of all points x and y such that the x coordinate, so these are x and y, they're the coordinates of any point inside this region, so that the x coordinate lies between negative 1 and 2. Okay, but now what's outstanding is the bounds for y. Okay, so remember the idea about Fubini's theorem and using slabs to approximate the volume. Right, so what we can do now is choose a value of x between negative 1 and 2 as our representative point and start drawing in rectangles. Okay, and remember how it works. The inner integral, right, in our iterated integral, we want to apply Fubini's theorem, turn that double integral into an iterated integral. The inner integral is just going to be the cross-sectional area of those slabs. Right? And so the bounds of that inner integral will just be the values, the lower and upper y values of these, the bases of these slabs. Okay? And so you can actually see for all cases, the lower bound always occurs on the parabola, which has equation y equals x squared. So therefore, any y value of a point inside our region must lie above y equals x squared, and the upper bound sits on this line y equals x plus 2. So the upper bound is therefore y equals x plus 2. Okay, so that gives us an expression for the region. Now here's why this process is so convenient, because now we've worked out an expression for the region in this way. Now we can apply Fubini's theorem. Okay, so that then implies that the double integral that we were given in the example can now be expressed as an iterated integral, which is 4x plus 10y. Now, the order of integration, because the y-coordinate is the one with the bounds that are functions of x, it means that's the one we're doing first. Okay, I mean, think of the interpretation in terms of slabs. The cross-sectional area, we're integrating in that inner integral, we're integrating from this lower bound of y and to this upper bound for y, both of which lie on these curves, which are the graphs of continuous functions of x. So if it's a type 1 region we're dealing with, it means we always integrate with respect to y first. Okay, so those two go hand in hand. So in this case, we're first integrating the function with respect to y from x squared to x plus 2, and then integrating with respect to x from negative 1 to 2. So remember, this is an iterated integral, so we work from the inside out. I guess I could put a bracket there just to indicate that. Okay, and so now evaluating that inner integral, we treat it just like a definite integral of a function of a single variable. So in this next line, we're going to evaluate that integral, and everything is going to occur inside this bracket. So everything is going to occur inside the integrand of that function, of that integral with respect to x. Okay, so we integrate partially with respect to y. What have we got? 4x plus 10y. So integrating that with respect to y, treating x as a constant, will give us 4xy plus 5y squared. But then that's evaluated from y equals x squared as the lower bound up to y equals x plus 2. Okay, so we treat this just like a definite integral. So when we when we substitute in those bounds, not 5, -1 to 2, we substitute the upper bound in first. So that's going to equal 4x times x plus 2. So I'm substituting in y equals x plus 2 first, plus 5 times x plus 2 all squared, minus the expression obtained when we substitute in the lower bound, which in this case is y equals x squared. So that's going to be 4x cubed plus 5. Now it's a y squared, so that's going to be x to the 4th. Okay, so this is all, as expected, this is all just a function of x now. So I could just expand that. It's polynomial in x, so the integration of that is not really difficult, right? So I won't go through the details of that. Leave it as an exercise. Check that the answer's 81. But look, for the purposes of this Math 2000 lecture now, I think the point has been made, right? I've shown you what type 1 regions are, and I've given you an example, shown you how to work out the bounds. That's always the hardest thing to do, in my opinion, is to work out the bounds of the iterated integral at the stage when we apply Fubini's theorem, right, at that step. Okay? So anyway, they're the type 1 regions. For the second type of region, we just rotate the picture 90 degrees. In other words, these are the regions that we can define between two constant values of y and between two continuous functions of y, or between the graphs of two continuous functions of y. So in this case, h1 of y and h2 of y. Okay, remember in this diagram, the positive x direction is to the right. So it's always this curve, the curve that's to the left, that provides the lower bound of x, and the curve on the right that provides the upper bound for x. Okay, so it's the same story, right? This is a special type of region, right? The type 2 regions that can be written in this way, or that can be expressed in this way, that sit between two constant values of y and these two curves defined in the form x equals h1 of y and x equals h2 of y. So once again, in terms of Fubini's theorem, we play this game with slabs, right? So we choose a representative point, or rather we divide the y-axis up into subintervals. Inside each subinterval, we choose a representative point that'll define or exactly where we are, or it'll define not only the bounds in that direction, right? It won't only define the base area of the slab, but it'll also define the top of the slab, because we evaluate our function of x and y, little f of x and y that we're integrating. We evaluate the function at that point, call it y star, and then the bounds of this rectangle in the xy plane would just be h1 of y star and h2 of y star. So now what we're doing is placing slabs on top of these rectangles in that direction that run along the x-axis. And now as we move up through the region, you can see that the length of the base of these slabs will change as we move. So we've got this additional complication. Right, but the cross-sectional area of the slabs in this case just works out to be an expression of this form, right, in that inner integral. Okay, and the width, I guess I should say the width of those slabs is the delta y. We sum up the approximation of all these slabs to get an approximation to the volume below the surface, and eventually take the limit as delta y goes to 0 to obtain this outer integral. But the inner integral is just the cross-sectional area of those slabs. Okay, it's just what we saw with Fubini's theorem, except now the only difference is is that the slabs are running lengthways parallel to the x-axis rather than the y-axis, as we saw in the previous example. Okay, so the important thing again is being able to express these type 2 regions in this form. And once again, the way we read such an expression is to say that the region consists of the set of all points with coordinates x and y, such that the y-coordinate is between, or lies between, the constant c and the constant d. And then given that value of y, the bounds for x will be h1 of y and h2 of y. Okay, so then, having such an expression for the region, we can then apply Fubini's theorem and just read off the bounds of that iterated integral. Okay, so in much the same way as we did for the type 1 regions. I've actually given another couple of diagrams of type 2 regions. Just one thing that I'll point out at this stage is this second diagram, the circle, I can consider that as either a type 1 or a type 2 region. So some regions in the xy plane can be both. All right? And in fact, as we'll see later, some can be neither. All right, so here's an example of a type 2 region. All right, so I mean, this is just very similar to the other example we worked through, just to really highlight the differences though. But there is a subtlety about this example. So now we want to evaluate this double integral, where the region of integration is just bounded by the line y equals x minus 1 and the parabola y squared equals 2x plus 6. So look, it's probably worthwhile drawing a diagram in the xy plane. So the parabola will look something like this. So I only just want to give a rough diagram, just showing what, in order to show what the region looks like. So this is y squared equals 2x plus 6. And we've also got the line y equals x minus 1. There's y equals x minus 1. Now, not a particularly good diagram, but not necessarily accurate, but close enough so we can see the region of integration lies between those two curves. Okay, so now the first thing, I can identify it as a type 2 region because I can see the lowest point on this region, namely the minimum value of y, will correspond to this point where the two curves intersect, and the maximum value will sit up here, again where the two curves intersect. So again, I can to work out the bounds for y, we work out the points of intersection of those two curves. Right, and so that's just, well, we've got y squared equals 2x plus 6. If I rearrange the second equation, write that as x equals y plus 1, and substitute it in. So substitute that in for x. So we have y plus 1. So we just have a quadratic to solve for y. So that implies we end up with y squared minus 2y minus 8 is 0. So y is going to be 4 or negative 2. So here's y equals negative 2. And here's y equals 4. They're not a particularly accurate graph, but nevertheless. So what we're saying is that the region can be expressed in this way as a set of all points with coordinates x and y, such that the y variable sits between negative 2 and 4. And then given any value of y in that range, all right, so just pick a value of y, so say this value here on the y-axis, we then look at the bounds for x. So that's where we can start placing our slabs parallel to the x-axis. Or in other words, just start drawing these. So these rectangles are intended to represent the bases of those slabs. All right, now remember the positive x direction is to the right. So I can see the lower bound for x. It's going to be to the left of the region, and I can see each of these rectangles I'm drawing inside the region. The leftmost points will lie on the parabola. Okay, and that parabola I can rearrange. So the equation is x equals, what would it be? So y squared minus 6 divided by 2. So a half times y squared minus 6. That's a half there. All right, so that's going to be the lower bound for x in that case, the equation of that parabola. Now to the right of those rectangles, right, they intersect with this straight line which has equation x equals y plus 1. So x equals y plus 1 is going to be the upper bound. So in that case, we've got an expression for the region, and we can apply Fubini's theorem easily now. So that means the double integral over d of this function xy is just going to become the iterated integral of xy, where now we're first integrating with respect to x between x equals a half y squared minus 6 up to y plus 1, and then with respect to y from negative 2 to 4. Okay, so just over the page. I mean, I won't work through this in its entirety. Just the next line, or the next couple of steps. It's just like evaluating an iterated integral. I could put a bracket around the inner integral. Remember, we work from the inside out. So I integrate partially with respect to x. So everything's going to happen inside this integral with respect to y. So now, integrating xy partially with respect to x, we treat y as a constant. So that's just going to be a half x squared y evaluated from x equals a half y squared minus 6 up to x equals y plus 1. Okay? And then we're treating it just like a regular definite integral. So substitute in the upper bound for x. So we'll get a half y plus 1 all squared times y minus the expression obtained when we substitute in that lower bound for x. So that's just a half y squared minus 6 all squared times y. Okay, now this is just a function of y. If I expand it out, it's just going to be a polynomial. And I won't go through those details, but just check that the answer is 36. Okay, there's one interesting point about this this example. So far, I've just talked about the application of volume below a surface. And if you remember, going right back to the start, I said, let's keep it simple and say the surface sits entirely above the xy plane. So in other words, the function only takes positive values on the over the region that we're considering. But in this case, remember the function that we're integrating is x times y. So look at the value of this function in the 4 quadrants of the xy plane. So in the positive quadrant, when x and y are both positive, x times y will be positive. When x and y are both negative, the function will also take on positive values. But now here, when y is positive and x is negative, the function actually takes on a negative value, which means the surface dips below the xy plane. Okay, similarly, for when x is positive and y is negative, in that quadrant, the function takes on negative values. So, how do we interpret this answer? What is it that we've just calculated? What does 36 represent? Okay, so far we've just been considering volume below a surface, but how do we interpret this result? Well, this is what I would call the net volume above the xy plane and below the surface z equals f of x and y. So by net volume, I mean the volume above the xy plane minus the volume of the solid part that sits below the xy plane. Right? And actually, I'll just point out that we can confer with, say, the graph of sine x. Sine x from 0 to 2 pi. Remember, if we integrate sine x from 0 to 2 pi, we get 0. So interpreting that in terms of area below a curve, how do we interpret that? Well, this is what we could call the net area. So it's just the area above the x-axis minus the area below. So this notion of net volume is completely analogous to this, right? So, I mean, it can happen that we get answers of 0 or even negative values for double integrals, and that's how we interpret them. All right, so I just want to point out some... so you see we're getting a bit more general, one step at a time now. Now we're dealing with functions that can take on negative values over our regions of integration. All right, just one last exercise. More complicated regions. How can we deal with them? So on page 67... So this region, this diagram I've got in the xy plane is actually neither type 1 nor type 2. But now we've seen the type 1 and type 2 regions, we can use those as the building blocks for more complicated regions. Right? And there's a property of, I'll just remind you, the properties of the double integral. Was it page 51? Can someone just check? Was it on page 51 of the workbook? Can someone just have a look? Is that where the properties are? There were 4 properties. And one is in the case where we write the region of integration as the union of 2 subregions, right? The disjoint union. Was that page 51? Anyone? Yeah. Okay, so it's the properties of the double integral on page 51. So for this complicated region, there are lots of ways we can deal with it, but here's one very simple way of dealing with it. If I draw a line across here at y equals 1, then I have divided this complicated region up into a type 1 region, which sits above the line, and a type 2 region, which sits below. So the entire region itself is neither type 1 nor type 2, but I can write it as the union of a type 1 region. I'll call that D1, and a type 2 region, which I'll call D2. All right, so D1 I can write as a set of all points x and y, so that x is between -1 and 1, and y is between 1, which is that line, and the parabola is the upper bound, which is x squared plus 1. And then D2, which sits below that line, y equals 1, is just defined as a type 2 region. So y sits between -1 and 1. Oops. And the x-coordinate is always sits to the right of -1 and to the left of this parabola x equals y squared. Okay, and then we use the properties on page 51, in particular, that the double integral can then just be written as a sum of the two double integrals over d1 and d2. And we can apply Fubini's theorem to both, right? So that first one, just reading off the bounds for x and y, plus now reading off the bounds for y and x, we can apply Fubini's theorem to the two individual parts. So this is just an example of how we can now use those building blocks to deal with more complicated regions by splitting the region up into either type 1 or type 2 subregions and dealing with each one separately and using this property of the double integral. Okay guys, so now we're pretty much armed and ready to start looking at some more applications. But next time I'm just going to look at one more thing, and that's how we can change the order of integration of an iterated integral from dx and dy to dy dx or vice versa. All right, see you next time.